Okay, so let's go over the introduction. So what are we gonna learn in this class? So let's write what we will learn. Learn in transport processes. Okay. Okay. So when we say transport processes, we mean the transport process, the transport of either energy or mass or it's momentum,
Yes.
right? Exactly. So we're gonna, I mean, the transport, when we say transport, we also mean the transport of momentum. Okay. In chemical engineering classes, when we say transport processes, we mean the transport of those three things. And mainly when we say energy, transport of energy, we mean the thermal energy generally. Not always, but it's the thermal energy generally what we mean as the transport of energy. Okay. And in fluid mechanics course, you have already seen the momentum transport in fluid mechanics course. And in this class, on the other hand, we're going to talk about particularly mass and thermal energy transport. This class. Okay. We can actually talk from time to time about momentum, but particularly we are interested in energy and mass transport in this class, in the context of this class. Okay. Any questions so far? Okay. And let's have some motivation. Why are we learning this? So when we say we're going to learn about transport of energy, mass, and momentum, we mean we're going to learn about the underlying equations, models that we can use, like useful models to understand the transport of energy, mass, and momentum. For example, we are going to talk about how the temperature is distributed within a solid body, how the mass is transported from one place to another, what is the rate of transport, like what is the flux of a particular species, what is the heat flux, and how we can actually make use of these knowledge to model or to design chemical engineering systems and to design, for example, reactors, heat exchangers, all useful equipment that we can use in the production of a product. Okay. So yeah, let's go on to motivation. Why are we learning it? Now, imagine that, suppose you would like to produce a product P, okay? And imagine that you have the reaction, you are given a reaction A goes to P, okay? Your reactants going to products, okay? And you have a reactor here, and you want to feed your A's, and you want to get a mixture of A's and P's. It might not be like the total conversion, but okay, so let me write this reactor correctly. Okay. But this reaction might happen, for example, at a particular temperature, say, for example, at 450 Kelvin, right? And maybe you're starting, I mean, you have some A here at room temperature. (300 Kelvin). But you want to actually feed it at 450 Kelvin, right? What do you need to do? You need to heat up the stream. You need to use what's called a heat exchanger, right? To heat the stream. So you need to use some like hot water or hot fluid or hot oil. And you actually cool down the oil to heat up the stream A, right? But when you have a look at this particular section, which is called a heat exchanger, you cannot just say, oh, I'm going to just heat up the stream, inlet stream, from 300 Kelvin to 450 Kelvin. You should actually come up with a device. You should tell what type of device you're going to use to make it possible, and you should actually come up with what is going to be the flow rate of the hot oil, what is going to be the size of the heat exchanger, right? And what is going to be the outlet oil temperature, and what inlet hot oil temperature is would be useful to use. Or necessary or required. You should answer all those questions. And to be able to answer all those questions, you need to model the system. So you need to know about the heat transfer. So that's one of the reasons that we learn about this. And by the way, everybody can hear me so far very well? Yes, no?
Yes.
Okay, good. And also, if you think about the mass transfer, you have a reactor here. Maybe you're using some catalysts in the reactor, right? You're going to learn about these catalysts and how to model reactors. But before, in the reaction class, in your senior year, but when you learn about that, you should be familiar with the particular mass transfer topics. For example, if you have a catalyst here, which has, for example, a diameter of d, this is your catalyst, and maybe the reaction is taking place in this catalyst, and maybe the reaction relies on the fact that the component A or the species A is diffusing into the catalyst, and the reaction is taking place there, and the product is coming out of the catalyst by diffusion, right? And in this perspective, in this view, you should be actually able to calculate the rate of flux of A into the catalyst. So you should answer, what is the flux of species A into catalyst particle? Because whatever you're gonna produce is gonna just depend on how much of A is actually entering into the catalyst particle. So you should be able to model the rate of flux, or the flux of A into the catalyst. And you should actually also answer the questions like, what is the concentration gradient profile, concentration profile within the catalyst. Okay, that's something you should be able to do to model a reactor. So basically, in order to be able to design reactors and heat exchangers, you need to know how to use the governing equations of transport processes. Okay, is that clear so far?
Yes, sir.
Okay, great. Now, so the idea is basically we want to learn the transport processes to be able to write down the governing equations for the transport of mass and heat as you did for the momentum in the fluid mechanics, right? In fluid mechanics, probably you were able to design pumps by knowing how much actually pressure drop you should actually impose on your system. And you were able to design the pipelines, right? The diameter of the pipe based on your fluid mechanics knowledge. You were able to design the pipes, calculate the diameter of the pipe, and use it in useful settings to produce a product. Okay. So at the end of this class, you will have learned the following: how to solve chemical engineering related problems, you will learn how to design heat and mass transfer equipment, and you will learn how to mathematically model the process of heat and mass transfer. The good news is the transport of heat transfer, mass transfer, and momentum transfer are analogous to each other, and the governing equations are very similar to each other. We will generally talk about the analogy between heat, mass, and momentum transfer. Okay, and one type of mathematical knowledge that you learn in that you learn to solve like heat transfer can be transferable to the problems that you solved mass transfer and momentum transfer. That's the good news. Okay, so we're going to deal with like similar mathematics and similar type of procedure, and you will learn how to, very importantly, you will learn how to do a shell balance. Have you learned this in fluid mechanics course, how to do a shell balance to solve chemical engineering problems? Anybody who can help me with that? Did you already learn shell balance? No. Okay, so this is a very powerful tool to solve chemical engineering problems, to actually generate differential equations to solve problems. Okay. Now, last part of the introduction, I'm going to talk about modes of heat transfer. Can you hear me, by the way?
Yes, sir.
Yeah.
Okay, great. Okay, modes of heat transfer. Now, there are three types of heat transfer. It can be conduction. So let's say three types. One is the conduction. The other is the convection. And the other one is radiation. Okay. When we say conduction, we mean the transport of the heat is being done by the collision of the molecules. Okay. Heat is transferred due to molecular collisions. Okay. Let me give you an example. Imagine that you have a metal bar here. And imagine that one side of it is kept hot end, and the other side is kept cold. And do you know which way that the heat is gonna be transferred? From hot end to cold end, or the cold end to hot end? Any guess?
Hot to cold.
Exactly. So the heat is being transferred from hot to cold. So this is going to be the direction of the heat transfer. And we call it the direction of conduction. So it's not convection, it's not radiation, it's conduction, because the mechanism that transfers the transport of the heat is by the collision of the molecules. So it's like the following. You can think about these molecules like crazily moving here, and imagine that the length of the okay, so the length of the arrow corresponds to the speed of the molecules, and you can actually correlate the heat, or the how hot the matter is, with the speed of the molecules. So if it has a higher temperature, the molecules have higher velocities. Here, the cold end, you're going to have smaller arrows because the velocities are smaller. Okay, but when you have like faster molecules colliding with slower molecules, then the slower molecules are going to get faster, and the faster molecules are going to get slower. There's going to be just averaging of these speeds. So that's why you're going to see the speed of the slower molecules are going to be faster with time. So that's why actually the heat is being transferred from left to right. So basically, the cold ones are getting hotter, the hot ones are getting colder by the molecular collisions. So if the mechanism is the molecular collisions, we call it conduction. Okay. And convection is basically the transfer of heat due to energy exchange between a surface and an adjacent fluid. Heat transfer due to energy exchange between a surface and an adjacent fluid. Okay. So an example is basically you have, imagine that you have a surface like a table or some sort of surface, okay, and you have air here, and then imagine that the surface is cold and then the air is hot, okay, and imagine that you're heating the table, the cold table, with the hot air. This is called convection. In convection, you have some sort of interface between two phases, but in conduction, you have one homogeneous material, or not necessarily homogeneous, but you're talking about one material, and the heat is being transferred due to the molecular collisions. But in convection, the heat transfer occurs between two different phases, between like two matter contacting each other, two different matter. And it can come in two forms. The convection can come in two forms. One is called natural convection. The other is called forced convection. Okay, and in natural convection, again, let's give this air and table example. In natural convection, you have this object, solid object, or maybe a table. You have this, again, air, but the air is stationary, not moving. Air is not moving, and the heat is being transferred from one to the other, either from the table to the air or from the air to the table, whatever. Heat is transferred. In forced convection, though, you have, again, the same setting, but the air is not stationary. Air is flowing. Maybe there's a wind, right? The air is flowing in one direction, but the heat transfer is still happening perpendicular to the surface. The black ones are the direction of the heat transfer, and the red arrow is the flow of the air. So the only difference between natural and forced convection is air is flowing in forced convection, or the gas or whatever your fluid is, it's moving. In the natural convection, air is stationary, or the fluid is stationary. And it doesn't necessarily be air. It can be a gas, any fluid, any liquid, anything that can flow. Okay. Any questions so far? Can you hear me?
Yes, sir.
Okay, great. Now the radiation. Okay, so we're going to talk about radiation. The heat can also transfer due to emission or absorption of photons. So let's write it down. Heat is transferred due to emission. Is emission with one M or two M's? Can anybody tell me what?
I think it's one M and two S's.
Two S's.
Two S's.
Excellent. Thank you. Emission. Yeah, emission or absorption of photons. Or photons means electromagnetic radiation, right? Okay. Okay. One fact about radiation is the following. Every object every object radiates heat. The reason is because every object has temperature. Since every object has a temperature. So if anything has a temperature, that radiates. And it's according to the formula that we're going to talk about later in more detail, but let me just give you the Q, the heat transfer rate or the radiation rate, it's called Q-rad, is equal to the area of the surface area of the object times epsilon, some constant, which is called emissivity, 1m. Sigma, which is the Stefan-Boltzmann constant, and times T to the power 4, the temperature of the object or the temperature of the surface. Object. Okay, so this formula tells you that if the temperature increases, the object radiates more heat. Can you give me any everyday example that you actually observe this phenomenon? Anybody who can give me an example?
Your phone?
What's it?
Your phone?
Yeah, our phone radiates, but it's not because it has a temperature. Like any object, for example, my coffee cup, you cannot see my camera, right?
No.
Okay, but anyway, I'm holding a coffee cup. It has some temperature and it radiates. And the reason why I don't see this radiation, although this is photons, and I mean, I can see like the light radiated from the sun and the lamps, but I cannot see the light that's radiated from the table, from my coffee cup, and so on. The reason is because of two things. First, the temperature is not high enough so that I can see, like I have like enough number of photons to be able to see. The second reason is the peak wavelengths that it radiates is not the visible wavelength. But if you increase the temperature of an object, then you start to actually see those photons. For example, if you heat a metal bar, really, I mean, if you, I don't know whether you have seen, but if you heat a metal bar, then you're gonna see that it's gonna go red, right? It's gonna radiate some heat. You're gonna see it like shining. And also the reason why we have the sunlight and we can see the sunlight is it's because it has an enormous temperature, and it's because these radiation is due to the sun's temperature. And the reason why a tungsten filament in lamps is shining is because it's heated up. There is no other reason. So you heat up a tungsten filament and you can see that it's shining. Okay, it's just a matter of temperature, and it's scaling with the fourth power of the temperature.